So in summary, we have the following result. LFP will not greater than Li minus PA. This is just what we proved. And the I minus PA, of course, will not greater than upper sum of I minus PA. And it also not greater than the lower sum of I plus PA. Okay, so this part, upper sum, because for the same function, lower sum and the same partition, lower sum will not will always be less than or equal to the upper sum. So L less than or equal to U is automatically true. And for this part is because I minus is not greater than I plus. Okay, because I minus is the lower integral of fxy dy, and I plus is the upper integral of the same function. So I minus x is not greater than I plus x. So for the same partition, larger function will have larger lower sum and a larger upper sum. Okay, so this justifies the second inequality in this step. This step. Okay. Now, we continue our estimate. The right hand side here. Will not greater than the upper sum of I plus PA. The reason is the same, okay? And the upper sum, for the upper sum, we just mentioned, upper sum of I plus will not greater than upper sum of F, okay? So we have this inequality. Now we can conclude our proof. Suppose F is integrable. Then for any epsilon positive, we can take a partition P of A cross B such that UFP minus LFP less than epsilon. Then for the corresponding partition PA, we mentioned given a partition of P, you will obtain the partition of A and B. Given partition of A cross B, you will obtain automatically partition of A and the partition of B. And the converse is also true. Suppose you partitioned A and B, then you will obtain the partition of A cross B automatically. Therefore, for the corresponding PA, by the above inequality, we obtain the I plus PA minus L I plus PA, because these two number is here. One is the red circle one, the other is this term. These two number lies between the upper sum and the lower sum of F. Therefore, the difference of here I will use blue, not blue. This term and this term lies between the upper sum and the lower sum of F. Therefore, the difference of these two terms will not greater than the difference of the lower sum and the upper sum of F. So this will not greater than Fp minus LFP, which is less than epsilon. So given epsilon positive, we can find a partition of A, that is PA. The PA is obtained by the partition of A cross B, that is P. Okay, so that the corresponding to this partition PA, the upper sum and the lower sum of I plus has difference less than epsilon. So this proves that I plus is integrable over A. Similarly, for I minus, the result is also true. Okay, so this proves the theorem. Okay, this proves our theorem. This proves the integrability of I plus and I minus. These two functions are integrable. This is part of the theorem. Here, the conclusion here has already proved. This should be integrable over A. But we still need to prove that the integral equalities to be true. Okay, but this is also not difficult. We will prove this. Now, for any epsilon positive, we can take a partition of A cross P. The partition is denoted by P. Such that the integral slightly decrease the integral will less than the lower sum, and the slightly increased integral will greater than the upper sum, because integral is the lower integral, which is the supplement of lower sum. Therefore, when slightly decrease, it will not be a upper bound of the lower sums anymore. Therefore, you have a partition greater than that. Okay. Then our previous computation tell us that this will not greater than the I plus PA, and this will not greater than the lower integral of I plus over A, and will not greater than the upper integral of I plus over A, and then this will not greater than the upper sum of I plus PA. Okay, but this upper sum will not greater than the upper sum of F. So we have this line. Okay, this is our step by step. So, but these two numbers are the same, because we already know that I plus is integrable. So these two numbers are the same. These two numbers are equal to the integral of I plus. Okay, so what this means? This means that we have this inequality. Now let epsilon goes to 0. We obtain our deserved result. That is okay. So this proves our theorem. Our theorem, of course, I just proved the equality for upper integral. Because I used I plus. Similarly, you can prove for lower integral, discussing with I minus. Okay, so this important theorem is proved. This theorem is called the Fubini theorem. If I am right, if I don't remember wrong, Fubini is an Italian mathematician. Okay, and when you maybe you must have another course, real analysis. In that course, you will study Lebesgue measure and the Lebesgue integral. Then you will encounter another the bigger version of Fubini theorem in that course. Okay. Now for this theorem, we have very some corollaries. Suppose A and B are rectangles of dimension n and n, and f is integrable. So if for any x in A, level change will obtain a function of y over b. This function is a function defined on b. The value of the function at y is fxy, right? So this function, for every x in A, this function is integrable on b. This is our assumption. Our Fubini theorem does not have this assumption. But once we have this assumption, then the result can be written by the difference of this corollary with the theorem is that in the theorem we have not assumed the integrability of this function for every x. Correspondingly, the inner integral makes no sense. Instead, we use the upper integral and the lower integral. Okay, but now since we add this assumption that the inner integral exists, therefore we don't need to work with upper and the lower integral, simply the usual integral. So this is the corollary. Okay. In particular, if f is continuous, f is continuous over the Cartesian product rectangle, of course it is integrable. And moreover, for any x in A, this function is also continuous over B. I use this letter to denote CE. CE to denote all the continuous function defined on E. Okay, therefore f belongs to, say, A cross B means that f is continuous over A cross B, over the Cartesian product rectangle. Then for every x in A, this function will be continuous over the rectangle B. Therefore, it is integrable. So we have another corollary. That is, if f is continuous over A cross B, then okay, we don't need to assume the integrability of the function, the f(x) dot mentioned in the previous corollary. Simply, the continuity of f give us the result immediately. And then you can also switch the order of integration. You can integrate with respect to x first and then y. Okay, so this is the Fubini theorem.